The stars are always there. Right now, as you listen to these words, thousands of distant suns hang in the space above you, their light traveling across incomprehensible distances to reach this planet. During the night, when darkness settles over your part of Earth, you can see them scattered across the sky, bright points of ancient light, some from stars that may no longer exist. But during the day, under the light of our own sun, those same stars become invisible. They haven't moved, they haven't dimmed. The photons from their surfaces are still streaming through space at 186,000 miles per second, still crossing the void, still entering Earth's atmosphere. Yet you cannot see them. This disappearance isn't magic. It's not a trick of perception or a failure of your eyes. The stars remain exactly where they've always been, continuing their patient vigil across the cosmos. The light from Sirius, 9 light-years away, still arrives. The glow from Betelgeuse, some 550 light-years distant, still makes its way through the dark. The photons from Rigel, approximately 860 light-years from Earth, still complete their centuries-long journey. But something happens in those last few dozen miles in the thin shell of gas that surrounds our planet. Something transforms the daytime sky from a window into deep space into an opaque vault of blue. Something fills the air with so much brightness that the distant stars, despite their genuine luminosity, cannot compete. The explanation involves the interaction between sunlight and the molecules that make up our atmosphere. It's a story about electromagnetic radiation, about the size of atoms compared to wavelengths of light, about the inverse relationship between wavelength and scattering efficiency. But more than that, it's a story about scale and brightness, about the overwhelming intensity of our nearest star compared to all the others, about the way matter bends and redirects light, turning our sky into a luminous dome during the day and allowing it to become a transparent window after sunset. The answer exists in the physics of light scattering, a phenomenon first mathematically described in the 19th century by British physicist John William Strutt, known as Lord Rayleigh. His equations revealed why our sky appears blue during the day and why sunsets paint the horizon in shades of red and orange. Those same principles explain why stars vanish from view when the sun rises and reappear when it sets. The mechanism is neither mysterious nor complex once you understand what's happening at the molecular level. It's actually quite elegant in its simplicity. But before we delve into the physics, before we examine the numbers and the wavelengths and the scattering coefficients, it helps to establish what we're really asking. The question isn't why stars are visible at night. That's the natural state. If you stood on the moon where there's no atmosphere, you could see stars at any time, whether the sun was above the horizon or not. The photographs taken by Apollo astronauts show a black sky even when the sun was brightly illuminating the lunar surface. The real question is why Earth's daytime sky isn't like that. Why does our atmosphere, that thin envelope of gas, create such different conditions between day and night? What is it about those molecules of nitrogen and oxygen, those atoms of argon, those trace amounts of carbon dioxide and water vapor that makes them transform the appearance of the sky? The phenomenon touches on several areas of physics and astronomy. It involves the spectrum of sunlight, the composition of our atmosphere, the way electromagnetic waves interact with matter, and the capabilities and limitations of human vision. It encompasses the brightness of the sun compared to other stars, the vast distances in space, and the relationship between wavelength and energy. Each piece contributes to the complete picture, and understanding one aspect helps illuminate the others. Throughout this exploration, we'll encounter specific numbers and measurements. The wavelengths of visible light, measured in nanometers. The composition of the atmosphere, described in percentages. The brightness of celestial objects, expressed using the magnitude scale. The intensity of sunlight, quantified in watts per square meter. These aren't abstract values, they're measurements of real physical properties, observations made through careful experiment and calculation. They help us understand not just what happens, but why it happens. Not just the effect, but the cause. The stars themselves haven't changed. They continue fusing hydrogen into helium in their cores, releasing enormous amounts of energy in the process. They continue radiating across the electromagnetic spectrum, sending light into space in all directions. Some of that light, after traveling for years or centuries or millennia, reaches Earth. During the night, when our location on the planet has rotated away from the sun, we can observe that stellar light directly. During the day, something intervenes. Something diffuses and redirects so much sunlight that the comparatively faint light of distant stars becomes imperceptible. This isn't a modern discovery. Humans have always known that stars disappear during the day and reappear at night. Ancient peoples tracked the motions of constellations across the seasons. They noted which stars rose just before dawn and which set just after dusk. They recognized the regular patterns, the predictable rhythms of the heavens. But understanding the mechanism behind these observations required scientific instruments and theoretical frameworks that only developed gradually over centuries. It required understanding the nature of light itself, the composition of the atmosphere, the physics of scattering. The explanation we'll explore isn't speculative or theoretical in the sense of being unproven. The mathematics of Rayleigh scattering have been confirmed countless times. The composition of Earth's atmosphere has been measured directly. The wavelengths of sunlight have been analyzed in detail. The brightness of stars has been catalogued with precision. These are established facts, verified through multiple methods, consistent across different observations. When we say that short wavelength light scatters more efficiently than long wavelength light, we're describing a measured phenomenon, not a hypothesis. When we note that the sun is approximately 400,000 times brighter than the full moon, we're stating an observational fact. The journey ahead will take us from the large scale, the sun, the atmosphere, the visible sky, down to the very small individual molecules, specific wavelengths, particular photons. We'll examine how light behaves when it encounters matter much smaller than its wavelength. We'll explore how the human eye responds to different levels of illumination. We'll calculate the relative brightness of different celestial objects. And gradually, piece by piece, the explanation will emerge. The mystery will resolve into clarity. But even as we understand the mechanism, the phenomenon itself retains a certain wonder. The fact that nitrogen and oxygen molecules, each just a few tenths of a nanometer across, can redirect sunlight so effectively that they fill the entire sky with blue light, that's remarkable. The fact that this same process, operating according to fixed physical laws, creates the beautiful gradients of color we see at sunrise and sunset, that's elegant. The fact that a simple change in the angle of sunlight, caused by Earth's rotation, can transform the sky from opaque to transparent. That demonstrates the delicate balance of conditions that shape our daily experience. So the stars remain where they've always been. Above you now, whether you can see them or not, Aldebaran in Taurus, 65 light-years away. Procyon in Canis Minor, 11 light-years distant. Arcturus in Bootes, 37 light-years from Earth. They're all there, all the time, their light continuously streaming toward us. The only thing that changes is our ability to perceive them, and that ability depends entirely on what's happening in the thin layer of gas between the stars and your eyes. During the day, that layer becomes filled with scattered sunlight, drowning out the fainter stellar sources. At night, without the sun to illuminate it, the atmosphere becomes transparent again, and the stars emerge. This is the essence of the explanation, but it's only the beginning. To truly understand why this happens, we need to examine each component in detail. We need to look at sunlight and see it not as simple brightness, but as a spectrum of wavelengths. We need to look at the atmosphere and see it not as empty space, but as a medium filled with countless trillions of molecules. We need to look at scattering and see it not as a vague concept, but as a precise physical interaction governed by mathematical relationships. Each layer of understanding adds to the picture, and by the time we're finished, the phenomenon that seemed puzzling will seem inevitable. This journey will unfold slowly and thoroughly. We're not racing toward a conclusion. There's no urgency here, no deadline to meet. The explanation exists in the details, in the careful examination of each component, in the patient building of understanding layer by layer. The pace will remain steady and calm throughout. There will be moments of concentrated information, but they'll arrive naturally without sudden shifts or dramatic revelations. Think of this as a gradual illumination rather than a sudden flash. The structure ahead moves from observation to explanation, from what we see to why we see it. We'll start with the visible phenomenon, the difference between the day sky and the night sky. Then we'll examine the source of daytime brightness, the sun and its radiation. From there, we'll explore the medium through which that radiation travels, the atmosphere and its composition. Then we'll investigate the interaction between radiation and atmosphere, the scattering process itself. Following that, we'll consider the receiver, the human eye and its capabilities. Finally, we'll bring all these elements together to show how they combine to create the effect we observe. Each section will provide the depth necessary for genuine understanding. This won't be a simplified explanation that glosses over the physics. We'll encounter wavelengths and intensities, compositions and percentages, equations and relationships. But these specifics aren't obstacles, they're the substance of the explanation. They transform vague concepts into precise knowledge. When you understand that blue light has a wavelength of approximately 420 nanometers, while red light has a wavelength of approximately 680 nanometers, and when you understand that scattering efficiency is inversely proportional to the fourth power of wavelength, you can calculate exactly why blue scatters more. The numbers provide clarity. The information presented comes from established scientific sources. The wavelength measurements derive from spectroscopic analysis. The atmospheric composition comes from direct sampling and analysis. The scattering mathematics come from Lord Rayleigh's original work in the 1870s, refined and confirmed by subsequent researchers. The stellar magnitudes come from centuries of careful astronomical observation. None of this is speculative. These are measured, verified facts about the physical world. When we discuss these topics, we're describing reality as accurately as current scientific understanding allows. You might find certain sections more detailed than expected. The explanation of Rayleigh scattering, for instance, will involve discussion of wavelength dependence and molecular polarization. The section on human vision will explore the differences between rod and cone cells, their spectral sensitivities, their different roles in daylight and nighttime vision. These details matter. They distinguish a thorough explanation from a superficial one. They allow you to understand not just the basic answer, but the complete mechanism. Not just what happens, but precisely how and why it happens. Throughout this exploration, you can simply listen. There's no need to visualize complex diagrams or follow intricate mathematical derivations. The language will describe the concepts clearly enough that imagination can fill in the details. When we discuss scattered light filling the daytime sky, you can picture that however you choose. Perhaps as countless tiny deflections, photons bouncing off air molecules in all directions, filling space with blue light. When we discuss stellar magnitudes, you can envision the difference between a bright star and a faint one, the way some stars stand out immediately while others require darker skies to become visible. The total journey will require about 2 hours of your attention. Some people will listen straight through, following the logical progression from start to finish. Others might drift in and out, catching certain sections in sharp focus while letting others wash over them more generally. Both approaches work. The explanation doesn't depend on holding every detail in memory simultaneously. The key insights will recur and reinforce themselves. The important relationships will appear multiple times in different contexts. By the end, understanding will have accumulated naturally rather than through forced concentration. If you're listening at night, perhaps before sleep, the calm pace and steady rhythm will support that purpose. The content is interesting enough to maintain attention, but delivered in a way that doesn't demand alertness. The voice will remain consistent, the energy level stable. There won't be sudden volume changes or tonal shifts. The information flows steadily, like a quiet stream, substantial but not turbulent, deep but not overwhelming. If you're listening during the day, perhaps while occupied with quiet tasks or simply resting, the same qualities apply. This isn't designed to excite or energize, it's designed to inform while maintaining tranquility. The wonder inherent in the subject matter, the physics of light, the vastness of space, the elegant simplicity of natural law, provides its own gentle fascination without requiring dramatic presentation. The sections ahead each serve a specific purpose in building the complete explanation. The discussion of sunlight establishes the source and nature of daytime illumination. The examination of atmospheric composition identifies the scattering medium. The explanation of Rayleigh scattering describes the interaction mechanism. The analysis of brightness level shows why stars can't compete with scattered sunlight. The exploration of human vision explains our observational limits. Each piece fits into the larger picture. Occasionally, we'll pause to consider implications or to connect one topic to another. These moments help maintain perspective, ensuring that individual facts don't become isolated details, but instead contribute to coherent understanding. When we finish discussing the scattering of blue light, for instance, we'll note how this relates to the appearance of the sky. When we examine the brightness of stars, we'll connect that to the question of visibility. These connections make the explanation cohesive rather than fragmentary. Some listeners will have background knowledge in physics or astronomy. For them, certain sections will serve as detailed confirmation of concepts they already understand generally. Others will encounter these ideas for the first time. The presentation accommodates both groups by maintaining thoroughness without assuming prior knowledge. Technical terms receive explanation when introduced. Concepts build from foundational principles. The logic proceeds step by step rather than making sudden leaps. The goal throughout is understanding rather than entertainment. This isn't a story with characters and conflict and resolution. It's an explanation of a natural phenomenon using the tools of physics and observational astronomy. The satisfaction comes not from narrative tension, but from intellectual clarity, from seeing how pieces fit together, from grasping the mechanism behind an everyday observation. You might notice that certain phrases or sentence structures repeat occasionally. This isn't accidental. Repetition aids comprehension, especially when listening rather than reading. Important concepts benefit from being stated in slightly different ways, allowing the mind to approach them from multiple angles. If a key relationship, such as the inverse fourth power wavelength, dependence of Rayleigh scattering, appears several times, that reinforces its centrality to the explanation. The transition between sections will be smooth rather than abrupt. One topic will lead naturally into the next. When we finish discussing the sun's radiation, we'll shift to how that radiation enters the atmosphere. When we complete our examination of atmospheric scattering, we'll move to how the scattered light affects visibility. The boundaries between sections exist for organizational clarity, but the explanation itself flows continuously. All of this sets the framework for what follows. The next sections will deliver on this promise of thorough, calm, clear explanation. The mystery of invisible daytime stars will resolve into comprehensible physics. The seemingly magical transformation of the sky from black to blue will become understandable as a consequence of molecular scattering. And through it all, the wonder of the phenomenon will remain intact even as its mechanism becomes clear. Consider the experience of watching dawn break. In the deep night, stars fill the sky above. Assuming you're far from city lights, thousands of them visible to the unaided eye. The Milky Way stretches across the heavens as a luminous band, the combined glow of billions of distant stars too faint to resolve individually. Individual bright stars stand out prominently. Sirius shines at magnitude -1.46, making it the brightest star in the night sky. Arcturus glows at magnitude -0.05. Vega shines at magnitude 0.03. These apparent magnitudes tell us how bright these stars appear from Earth, with lower numbers indicating greater brightness and negative numbers indicating the very brightest objects. As dawn approaches, the eastern horizon begins to lighten. This happens before the sun itself rises, while it's still below the horizon. The light comes from sunlight hitting the upper atmosphere, where air molecules scatter some of that light downward. The scattered light gradually fills more and more of the sky as the sun approaches the horizon. This is twilight, the transition period between full night and full day, or between full day and full night. During twilight, you can observe the gradual disappearance of stars. They don't vanish all at once. The faintest stars become invisible first. A star of magnitude 6.0 or 6.5, barely visible even in dark rural skies, disappears while many brighter stars remain visible. Then stars of magnitude 5 become hard to see. Then magnitude 4. The process continues as the sky brightens. The brightest stars hold on longest. You can still see Sirius and Vega and the brightest planets after many other stars have faded from view. But eventually, as the sun crests the horizon and full daylight arrives, even these brilliant objects become invisible against the bright blue sky. The transition operates in reverse at dusk. As the sun sets and twilight begins, the sky gradually darkens. The brightest stars and planets appear first. Venus, if it's in the evening sky, might become visible before sunset, shining at magnitude -4.6 or brighter. Jupiter follows, at magnitude -2.7. Then, the brightest stars appear. As twilight deepens and the sky darkens further, progressively fainter stars become visible. By the time full night arrives, the complete stellar vista has emerged. This daily cycle, stars visible at night, invisible during day, is so familiar that we rarely pause to question it. But the stars themselves haven't changed. Their actual luminosity, the total energy they radiate per unit time, remains constant. Betelgeuse, a red supergiant in Orion, radiates approximately 140,000 times more energy than the Sun. That enormous output continues whether we can see it or not. The light from Betelgeuse, having traveled across approximately 550 light-years of space, arrives at Earth continuously. At night, we can see it easily. During the day, it vanishes. The difference isn't in the stars, it's in what's happening between the stars and our eyes. During the night, light from stars travels through space and then through Earth's atmosphere with minimal interference. Some absorption and scattering occurs. Our atmosphere isn't perfectly transparent, but most of the starlight reaches the ground. During the day, something fills the atmosphere with light so bright that starlight, still present, becomes imperceptible by comparison. That something is scattered sunlight. The Sun, our nearest star, lies approximately 93 million miles from Earth. At that distance, the Sun appears as a disk roughly half a degree in diameter, about the same apparent size as the full moon. Despite being just one star among hundreds of billions in our galaxy, the Sun dominates Earth's sky because of its proximity. The inverse square law governs how brightness decreases with distance. If you double the distance to a light source, its apparent brightness decreases by a factor of 4. If you increase the distance by 10 times, the brightness decreases by a factor of 100. The Sun is so much closer than any other star that this relationship makes it overwhelmingly brighter than all of them. The Sun's apparent magnitude, as seen from Earth, is approximately -26.7. Compare that to Sirius at -1.46. The magnitude scale is logarithmic, with each step of 5 magnitudes representing a factor of 100 in brightness. The Sun is therefore approximately 25 magnitudes brighter than Sirius. Working through the mathematics, 25 magnitudes equals 5 steps of 5 magnitudes each, which means 5 factors of 100, which equals 10 billion. The Sun appears approximately 10 billion times brighter than Sirius, the next brightest star in our sky. This enormous difference in apparent brightness is the foundation of the phenomenon. If the Sun were only slightly brighter than other stars, the daytime sky might still allow us to see them. But the Sun is billions of times brighter, and this vast disparity creates conditions where sunlight completely overwhelms starlight during the day. The mechanism by which this happens involves the scattering of sunlight by atmospheric molecules. But the underlying reason the mechanism succeeds is the sheer intensity difference between sunlight and starlight. At dawn, as the Sun rises, its light begins flooding into the atmosphere. Even before the Sun becomes visible, when it's still below the horizon, its light is illuminating the upper atmosphere. That light scatters, some of it redirected downward. This scattered light brightens the sky. As the sky brightens, it eventually becomes brighter than the light arriving from distant stars. When that happens, the stars disappear from view. Not because they've stopped shining, not because their light has stopped arriving, but because our eyes can no longer distinguish their faint light against the bright background. The process is analogous to trying to see a candle flame in a brightly lit room. In darkness, even a small candle is easily visible. Its flame stands out clearly against the black background. But in a well-lit room, that same candle flame becomes difficult to see. The flame hasn't changed. It's producing the same amount of light. But that light now competes with all the other light in the room, and it no longer stands out against the background. Our eyes detect contrast, differences in brightness between objects and their surroundings. When the background brightness approaches or exceeds the brightness of an object, that object becomes invisible even though it's still emitting or reflecting light. During the day, Earth's atmosphere becomes like that brightly lit room. The room is filled with scattered sunlight, creating a bright blue background. Stars, like candle flames, continue producing light, but that light doesn't create enough contrast against the bright sky to be perceived. At night, the room goes dark. The atmosphere no longer scatters sunlight because the sun is below the horizon. The background becomes black. Against that dark background, even relatively faint stars create sufficient contrast to be visible. The question of why this happens, why the atmosphere fills with scattered light during the day, requires examining the nature of light itself, the composition of the atmosphere, and the physics of light-matter interaction. But before we delve into those details, it's worth appreciating the elegance of the basic observation. The stars are always there. The variation isn't in their presence, but in their visibility. And that visibility depends on what's happening in the thin shell of gas that surrounds our planet. The atmosphere itself is remarkably thin compared to the size of Earth. The troposphere, where most scattering occurs, extends only about 7 to 12 miles above the surface. The planet's radius is approximately 4,000 miles. If you scaled Earth down to the size of an apple, the atmosphere would be about the thickness of the apple's skin. This thin layer, this delicate envelope of gas, is what stands between us and direct observation of space. At night, it becomes essentially transparent. During the day, it becomes opaque with scattered light. The transition at dawn and dusk occurs gradually rather than instantaneously because the sun doesn't simply appear or disappear, but rather crosses the horizon over a period of minutes. As it does, the angle at which its light enters the atmosphere changes. When the sun is below the horizon, its light must travel through more atmosphere to reach your location, which means more scattering occurs. This creates twilight. When the sun is just above the horizon, its light still travels through a considerable amount of atmosphere at a shallow angle. As the sun rises higher, the path length through the atmosphere decreases, and the amount of scattering actually decreases per unit distance, but the total amount of light entering the atmosphere increases because the sun is no longer partially blocked by the horizon. This daily cycle has shaped human experience throughout history. Before artificial lighting, the visibility of stars governed nighttime activities. Navigation, both over land and sea, relied on stellar positions. Agricultural societies tracked seasonal changes by noting which constellations were visible at different times of year. The apparent motion of the stars across the sky, caused by Earth's rotation, provided a natural clock. All of this depended on the stars being visible at night and invisible during day, creating a clear distinction between the nighttime sky and the daytime sky. Even now, in an era of artificial lighting and digital timekeeping, the distinction between day and night remains fundamental to human experience. We're diurnal creatures, active during the day when our visual system works best, resting at night. The change in the sky's appearance reinforces this daily rhythm. The bright blue sky of midday signals full daylight. The starry sky of midnight signals deep night. The transitional periods of dawn and dusk, when stars gradually appear or disappear, mark the boundaries between these states. So the morning mystery, the gradual disappearance of stars as dawn approaches, isn't really mysterious once you understand what's happening. The stars don't leave, they don't dim. their light continues arriving at Earth in the same quantities as before. What changes is the state of the atmosphere, which transforms from a transparent medium at night into a light-filled medium during day. This transformation occurs because of the scattering of sunlight by air molecules, a process we'll now examine in detail. Light is electromagnetic. Radiation, a wave of oscillating electric and magnetic fields that propagates through space at approximately 186,000 miles per second. This speed, usually denoted by the letter c, is a fundamental constant of nature. All electromagnetic radiation travels at this speed in vacuum, regardless of wavelength or frequency. The relationship between wavelength and frequency is simple. The product of wavelength and frequency equals the speed of light. If you know the wavelength, you can calculate the frequency and vice versa. Visible light occupies a small portion of the electromagnetic spectrum, ranging from approximately 390 nanometers at the violet end to approximately 700 nanometers at the red end. A nanometer is 1/1,000,000th of a meter. To put this in perspective, a typical human hair is approximately 80,000 to 100,000 nanometers in diameter. The wavelengths of visible light are incredibly small, far smaller than the objects we encounter in daily life. The sun radiates across a broad spectrum of wavelengths, not just visible light. At the surface of the sun, temperatures reach approximately 5,800 degrees Kelvin. At this temperature, the sun's spectrum peaks in the visible range, though it extends into the ultraviolet at shorter wavelengths and the infrared at longer wavelengths. The distribution of energy across different wavelengths follows what's called a blackbody spectrum, which depends solely on temperature. Hotter objects emit more energy at shorter wavelengths. Cooler objects emit more at longer wavelengths. When sunlight reaches the top of Earth's atmosphere, it has an intensity of approximately 1,361 watts per square meter. This value, known as the solar constant, represents the power per unit area of sunlight at Earth's orbital distance from the sun. The measurement is perpendicular to the sun's rays. Imagine a 1 meter by 1 meter panel facing directly toward the sun. That panel receives approximately 1,361 watts of power. Not all of this radiation reaches Earth's surface. As sunlight passes through the atmosphere, several processes reduce its intensity. Some radiation is absorbed by atmospheric gases. Ozone in the stratosphere absorbs most ultraviolet radiation with wavelengths shorter than about 300 nanometers. Water vapor and carbon dioxide absorb radiation in certain infrared wavelengths. Oxygen absorbs some ultraviolet. These absorption processes convert electromagnetic energy into heat, warming the atmosphere. Some radiation is reflected back to space by clouds, aerosols, and atmospheric particles. This reflected radiation never reaches the surface. The amount of reflection depends on cloud cover and atmospheric conditions. On a clear day, reflection is minimal. On an overcast day, thick clouds can reflect a substantial fraction of incoming sunlight, and some radiation is scattered by air molecules and particles. This is the process most relevant to our question about invisible stars. Scattering redirects light without absorbing it. A photon traveling in one direction encounters an air molecule and gets deflected to a new direction. The photon doesn't lose energy in this process. It's elastic scattering, but its direction changes. When billions upon billions of photons get scattered in random directions, the effect is to fill the atmosphere with light coming from all angles, not just directly from the sun. On a clear day, approximately 1,000 watts per square meter of solar radiation reaches Earth's surface at sea level when the sun is directly overhead. This is slightly less than the 1,361 watts per square meter at the top of the atmosphere, reflecting the losses to absorption, reflection, and scattering. At lower solar angles, when the sun is near the horizon, the intensity is much less because sunlight must travel through more atmosphere. The atmosphere itself consists primarily of nitrogen and oxygen. Dry air is approximately 78% nitrogen, 21% oxygen, and about 1% argon by volume. These three gases account for more than 99% of the atmosphere. The remaining fraction includes carbon dioxide, neon, helium, methane, and other trace gases. Water vapor, which varies geographically and temporally, can account for up to 4% of the atmosphere in humid tropical regions, but is nearly absent in cold, dry areas. The molecules of nitrogen and oxygen are very small. A nitrogen molecule, consisting of two nitrogen atoms bonded together, has a diameter of approximately 0.3 nanometers. An oxygen molecule, also consisting of two atoms, is similarly sized. Recall that visible light has wavelengths ranging from about 390 to 700 nanometers. The atmospheric molecules are therefore hundreds of times smaller than the wavelengths of visible light. This size relationship is crucial to understanding scattering. The atmosphere is also remarkably dense with molecules. At sea level, standard atmospheric pressure is approximately 101,325 pascals, or about 14.7 pounds per square inch. At these conditions, 1 cubic meter of air contains approximately 2.5 times 10 to the 25th power molecules. That's 25 followed by 24 zeros, an enormous number. Even though individual molecules are incredibly tiny, the sheer quantity of them in even a small volume of air means that light traveling through the atmosphere encounters countless molecules. The troposphere, the lowest layer of the atmosphere where virtually all weather occurs and where most scattering takes place, extends from the surface to an altitude of approximately 7 to 18 kilometers, depending on latitude. It's thickest at the equator and thinnest at the poles. This layer contains about 75 to 80% of the atmosphere's total mass. Above it lies the stratosphere, extending to about 50 kilometers, which contains the ozone layer. Above that lie the mesosphere, thermosphere, and exosphere, but these upper layers are so thin that they contribute little to scattering of visible light. When a photon of sunlight enters the atmosphere, it begins a journey through this dense field of molecules. For most photons, the journey from the top of the atmosphere to the surface is direct. They travel straight down without interacting with any molecules. The atmosphere, despite its molecular density, is mostly empty space at the scale of photons. But some photons do interact. They encounter nitrogen or oxygen molecules and get scattered. The probability of scattering depends on wavelength. This is the key insight, first quantified by Lord Rayleigh in the 1870s. Rayleigh was investigating why the sky appears blue, and his mathematical analysis showed that the amount of scattering is inversely proportional to the fourth power of the wavelength. This means that if you halve the wavelength, the scattering increases by a factor of 2 to the fourth power, which equals 16. Blue light, with its shorter wavelength, scatters much more efficiently than red light with its longer wavelength. Consider blue light at approximately 450 nanometers and red light at approximately 650 nanometers. The ratio of wavelengths is 650 divided by 450, which is approximately 1.44. The scattering ratio is the fourth power of this, which is approximately 4.4. Blue light scatters about 4.4 times more efficiently than red light. If you compare violet light at 400 nanometers to deep red at 700 nanometers, the wavelength ratio is 1.75, and the scattering ratio is approximately 9.4. Shorter wavelengths scatter much more than longer wavelengths. This wavelength dependence explains why the sky appears blue rather than white or red or any other color. When white sunlight, containing all visible wavelengths, enters the atmosphere, the short wavelength blue and violet components scatter more strongly than the long wavelength red and orange components. The scattered light, coming from all directions rather than directly from the sun, enriches in the short wavelength colors. Our eyes perceive this as blue. The sun itself appears slightly yellower than it would in the absence of an atmosphere because some of the blue light has been scattered away from the direct beam. The scattering is even stronger for violet light than for blue light, yet the sky appears blue rather than violet. This occurs partly because the sun emits less violet light than blue light to begin with, and partly because the human eye is less sensitive to violet wavelengths than to blue wavelengths. The peak sensitivity of human color vision under daylight conditions occurs around 550 nanometers in the green-yellow region. Our sensitivity decreases toward both the red end and the blue end of the spectrum, with the decrease being more pronounced toward violet. The scattered blue light fills the entire sky because scattering occurs at all altitudes throughout the atmosphere. When you look at any point in the sky away from the sun, you're seeing sunlight that has been scattered by air molecules in that direction. The molecules don't emit light themselves. They're redirecting sunlight that's passing through the atmosphere. This redirection occurs countless times per second as photons interact with molecules, and the cumulative effect is to distribute blue light throughout the sky dome. The intensity of this scattered light depends on several factors. It depends on the intensity of incoming sunlight, which varies with the angle of the sun above the horizon. It depends on the length of the path through the atmosphere, which also varies with solar angle. It depends on atmospheric conditions, humidity, aerosols, pollutants, all of which affect both scattering and absorption. But under typical clear sky conditions during midday, the scattered light is bright enough to create a vivid blue sky. This bright sky is what makes stars invisible during the day. The stars are still emitting light, still sending photons toward Earth, but those photons must compete with all the scattered sunlight filling the atmosphere. When you look toward a star during the day, you're looking through a volume of air that's glowing with scattered blue light. The star's light must stand out against that glowing background, and in most cases, it cannot. To understand why atmospheric molecules scatter light, we need to examine what happens when electromagnetic radiation encounters matter much smaller than its wavelength. This is the regime of Rayleigh scattering, named after Lord Rayleigh, who first developed the mathematical theory in 1871 while investigating the color of the sky. His work revealed a fundamental relationship between wavelength and scattering efficiency, a relationship that explains not only why the sky is blue, but also why sunset appears red and why stars vanish during the day. Light consists of oscillating electric and magnetic fields. As a light wave passes by an atom or molecule, the oscillating electric field exerts forces on the charged particles within that atom or molecule. The electrons, being much lighter than the nucleus, respond to these forces by oscillating at the same frequency as the light wave. This creates a small oscillating electric dipole. Essentially, the electron cloud shifts back and forth relative to the nucleus. An oscillating electric dipole radiates electromagnetic waves. This is a fundamental result from classical electromagnetism. When charges accelerate, they produce electromagnetic radiation. The oscillating electrons in the molecule, driven by the incoming light wave, become tiny antennas that broadcast electromagnetic waves in all directions. This radiated energy is the scattered light. The molecule absorbs energy from the incoming light wave and re-radiates it in different directions. The crucial insight is that the strength of this scattering depends on the wavelength of the light. Shorter wavelengths, with their higher frequencies, cause more rapid oscillations of the electron cloud. More rapid oscillations mean greater acceleration of the charges. Greater acceleration produces stronger radiation. The mathematical analysis shows that the scattered intensity is proportional to the fourth power of the frequency, or equivalently, inversely proportional to the fourth power of the wavelength. This fourth power relationship creates dramatic differences in scattering efficiency across the visible spectrum. As we calculated earlier, blue light at 450 nanometers scatters about 4.4 times more than red light at 650 nanometers. Violet light at 400 nanometers scatters about 9.4 times more than deep red at 700 nanometers. These aren't small differences. They're large enough to completely change the color composition of scattered light compared to the original sunlight. When white sunlight enters the atmosphere, it contains roughly equal amounts of energy across the visible spectrum. The sun's blackbody spectrum peaks in the green around 500 nanometers, but there's substantial energy at all visible wavelengths. As this light travels through the atmosphere, the short wavelength components scatter preferentially. After the light has traveled through enough atmosphere that scattering becomes significant, the forward beam, the light traveling in the original direction from the sun, has lost more, blue and violet, than red and orange. Meanwhile, the scattered light, the light deflected to other directions, contains more blue and violet than red and orange. This explains two related phenomena simultaneously. First, it explains why the sky appears blue. When you look at the sky away from the sun, you're seeing scattered light, which is enriched in short wavelengths. Second, it explains why the sun appears yellowish, especially when low in the sky. The direct sunlight has lost some of its short wavelength components to scattering, shifting its apparent color toward the red end of the spectrum. The effect becomes more pronounced when sunlight travels through more atmosphere. When the sun is directly overhead at noon, sunlight travels through the minimum possible thickness of atmosphere, approximately straight down through the troposphere. The path length through the atmosphere is perhaps 8 to 10 kilometers. When the sun is near the horizon at sunrise or sunset, sunlight travels through the atmosphere at a shallow angle. The path length can be 30 or 40 times longer. This longer path means much more scattering. With extensive scattering, nearly all the short wavelength light gets redirected away from the direct beam. The sun itself appears red or orange, because that's what's left after the blue and green have been scattered away. The sky near the sun at sunset can show beautiful gradients of color, red and orange nearest the sun, transitioning to yellow, then to blue overhead. These colors map the varying amounts of scattering experienced by light coming from different directions. The mathematics of Rayleigh scattering applies specifically to particles much smaller than the wavelength of light. The rule of thumb is that the particle must be smaller than about 1/10 the wavelength. For visible light with wavelengths of 400 to 700 nanometers, this means particles smaller than about 40 to 70 nanometers. Nitrogen and oxygen molecules at about 0.3 nanometers are well within this regime. They're hundreds of times smaller than the wavelength, making Rayleigh scattering the appropriate description. For larger particles, different scattering behavior occurs. When particles approach the size of the wavelength or become larger, we enter the regime of Mie scattering, named after Gustav Mie, who solved the more general scattering problem in 1908. Mie scattering doesn't have the strong wavelength dependence of Rayleigh scattering. For particles much larger than the wavelength, scattering becomes essentially independent of wavelength. This is why clouds appear white. The water droplets in clouds are much larger than light wavelengths, so they scatter all colors equally. The scattered light retains the white color of sunlight. The distinction between Rayleigh and Mie scattering is important for understanding different atmospheric phenomena. The blue sky is pure Rayleigh, scattering from molecules. The white clouds are primarily Mie, scattering from droplets. Haze and fog involve scattering from particles of intermediate size, producing effects that blend Rayleigh and Mie characteristics. Smoke and dust can produce various colors depending on particle size distribution. For our question about star visibility, Rayleigh scattering is the dominant process. The molecules that make up 99% of the atmosphere, nitrogen, oxygen, argon, are all small enough that they scatter according to Rayleigh's equations. Even water vapor molecules, when present as individual molecules rather than condensed droplets, participate in Rayleigh scattering. The result is that clear air scatters sunlight according to the inverse fourth power law, creating the blue sky we observe. The intensity of Rayleigh scattered light depends not just on wavelength, but also on the number density of molecules. More molecules mean more scattering. This is why the sky appears deeper blue when viewed from high altitudes. There's less atmosphere above you, so less scattering occurs, and the sky begins to take on the blackness of space. At the cruising altitude of commercial aircraft, around 10 kilometers, about 75% of the atmosphere lies below. The sky viewed from that altitude appears darker blue than from sea level. The amount of scattering also depends on the scattering angle, the angle between the incoming sunlight direction and the direction of observation. Rayleigh scattering produces scattered light in all directions, but the intensity varies with angle. Forward scattering and backward scattering have higher intensities than scattering at right angles. However, this variation is not extreme, and for our purposes, we can think of the scattering as roughly uniform in all directions. When sunlight enters the atmosphere, photons begin scattering almost immediately. Some photons scatter after traveling just a few meters. Others travel kilometers before scattering. Some photons never scatter at all, traveling straight down to the surface. The probability of scattering depends on the number of molecules encountered, which depends on both the density of the atmosphere and the distance traveled. On average, a photon of blue light travels farther through the atmosphere before scattering than a photon of red light. But the distances are long compared to the thickness of the atmosphere, so most photons reach the surface without scattering. Yet even though most photons don't scatter, enough do that the cumulative effect is substantial. When you have billions of photons entering the atmosphere every second, even a small scattering probability produces enormous amounts of scattered light. The sky doesn't appear dimly blue, it appears vividly blue because the sheer intensity of sunlight creates vast quantities of scattered light, even though the scattering probability per photon is low. The blue light scattered by atmospheric molecules becomes the background against which we would need to see stars during the day. This scattered light comes from all directions. When you look toward the zenith, you're looking through perhaps 10 kilometers of atmosphere, and throughout that volume, molecules are scattering blue light toward your eyes. When you look toward the horizon, you're looking through much more atmosphere at a shallow angle, perhaps hundreds of kilometers, and all that atmosphere is contributing scattered light. The brightness of this scattered light, measured at the surface, depends on conditions. On a clear day with the sun high in the sky, the zenith sky might have a brightness of roughly 10,000 to 15,000 candelas per square meter. A candela is a unit of luminous intensity, and a candela per square meter, also called a nit, measures luminance, the brightness of an extended source like the sky. For comparison, a typical computer monitor might have a brightness of 200 to 300 candelas per square meter. The daytime sky is much brighter than most artificial displays. Against this bright background, stars must compete. A star's light must produce enough illumination at your eye to be distinguished from the background brightness. During the night, the background is essentially black, perhaps a fraction of a candela per square meter in the darkest locations. Even a modest star produces enough contrast to be visible. During the day, the background is tens of thousands of times brighter. Only the most luminous objects can produce sufficient contrast. The sun itself, of course, remains easily visible. Its brightness is so extreme that even the scattered sunlight filling the sky doesn't come close to matching it. Looking directly at the sun can damage your eyes precisely because its brightness is so far beyond the normal range. The sun's disk has a luminance of approximately 1,600,000,000 candelas per square meter, about 100,000 times brighter than the surrounding sky. This enormous difference allows the sun to stand out clearly despite the scattering that it itself causes. The moon, when visible during the day, can sometimes be seen, though often faintly. The full moon has an apparent magnitude of about -12.6, making it far dimmer than the sun, but bright enough in many cases to show contrast against the daylight sky, especially when the sky is not at its brightest, such as when the sun is lower in the sky or when the moon is high overhead. A crescent moon is harder to see during the day because its smaller illuminated area spreads its light over a larger angle, reducing its surface brightness. The brightest planets can sometimes be seen during the day if you know exactly where to look. Venus at its brightest reaches magnitude -4.6. With careful searching under ideal conditions, clear skies, Venus high above the horizon, positioned away from the sun, the planet might be spotted as a faint white dot against the blue sky. Jupiter at magnitude -2.7 is more challenging but not impossible. These observations require favorable conditions and often benefit from knowing precisely where to look, but they demonstrate that very bright objects can produce enough contrast even against the scattered sunlight. For stars, however, the task is essentially impossible. The brightest stars like Sirius at magnitude -1.46 even under the most perfect conditions, lack the intensity to create visible contrast against the daytime sky. The scattered sunlight simply overwhelms their faint light. This is the mechanism that makes stars invisible during the day, not that their light fails to arrive, not that the atmosphere blocks it completely, but that the scattered sunlight creates a bright background against which stellar light cannot produce perceptible contrast. To understand why stars vanish, during the day we need to quantify the brightness levels involved. Astronomy uses the magnitude scale to describe apparent brightness, with smaller numbers indicating brighter objects and negative numbers indicating the very brightest. The scale is logarithmic. A difference of 5 magnitudes corresponds to a factor of 100 in brightness. Each magnitude step represents a brightness factor of approximately 2.512. The Sun's apparent magnitude is approximately -26.7. Sirius, the brightest star in the night sky, has an apparent magnitude of approximately -1.46. The difference is about 25.2 magnitudes. To calculate the brightness ratio, we divide this by 5 to get the number of 5 magnitude steps. 25.2 divided by 5 equals about 5.04. Each 5 magnitude step represents a factor of 100, so 5.04 steps represents 100 to the 5.04 power, which equals approximately 11 billion. The Sun appears roughly 11 billion times brighter than Sirius. This vast disparity in apparent brightness results from the proximity of the Sun. In terms of intrinsic luminosity, the total energy radiated per unit time, many stars far exceed the Sun. Betelgeuse radiates approximately 140,000 times more energy than the Sun. Rigel radiates about 120,000 times more. Deneb radiates approximately 200,000 times more. But these stars lie hundreds of light years away, while the Sun is merely 8 light minutes away. Distance reduces apparent brightness according to the inverse square law, making even these luminous giants appear faint compared to our nearby Sun. The full moon, for comparison, has an apparent magnitude of approximately -12.6. The Sun is therefore about 14 magnitudes brighter than the full moon. 14 magnitudes divided by 5 equals 2.8 magnitude steps of 5 each, which represents 100 to the 2.8 power, or about 400,000. The Sun appears roughly 400,000 times brighter than the full moon. You can see the full moon easily at night because it's bright enough to produce strong contrast against the dark sky. During the day, when the sky fills with scattered sunlight, the moon becomes much harder to see, though it's still possible under good conditions because the moon's surface brightness, concentrated in its small disk, can exceed the brightness of the surrounding sky. Stars present a different challenge. Unlike the moon, which appears as an extended disk, stars appear as point sources. Even through large telescopes, stars remain points of light rather than resolved disks. Their light arrives from a single direction rather than from an extended area. This matters because contrast detection works differently for point sources than for extended sources. The human eye is somewhat more sensitive to point sources against a uniform background, but stars must still produce enough brightness to be detected. The typical limiting magnitude for naked eye observation under good dark sky conditions is approximately 6.0 to 6.5. This means stars fainter than magnitude 6.5 are not visible to the unaided eye, while stars brighter than magnitude 6.0 are readily visible. Under urban conditions with significant light pollution, the limiting magnitude might be only 4.0 or even 3.0, meaning only the brightest few hundred stars remain visible. During the day, the limiting magnitude becomes extremely poor, typically better than -4 or so, meaning only objects brighter than magnitude -4 can be seen. This eliminates all stars and most planets. Venus at its brightest can reach magnitude -4.6, placing it just barely at the threshold of daytime visibility under ideal conditions. Jupiter at -2.7 and Mars at its brightest at -2.9 fall short. Saturn, Mercury, and all stars are far too faint. The daytime sky brightness varies with solar elevation and atmospheric conditions. When the sun is directly overhead at noon under clear skies, the sky is at its brightest. The zenith, the point directly overhead, appears as the darkest part of the daytime sky because you're looking through the minimum amount of atmosphere. Near the horizon, you're looking through much more atmosphere at a shallow angle, and both scattering and atmospheric haze make the horizon sky appear brighter and whiter. Measurements of sky brightness at the zenith on clear days with the sun high typically yield values around 10,000 candelas per square meter, though this can vary from about 8,000 to 15,000 depending on conditions. Near the horizon, brightness can increase to 20,000 or even 30,000 candelas per square meter as multiple scattering and aerosol effects become significant. To put these numbers in perspective, a typical indoor room might have an illumination level of 300 to 500 lux. 1 lux is 1 lumen per square meter, where a lumen measures luminous flux, the total visible light emitted by a source weighted by human eye sensitivity. The sun at the zenith produces an illumination of approximately 100,000 lux at Earth's surface. The full moon produces about 0.2 lux. This factor of 500,000 in illumination level explains why daytime and nighttime feel so different visually. The human eye is remarkably adaptable to different light levels. The pupil can vary in diameter from about 2 millimeters in bright light to about 8 millimeters in darkness, changing the amount of light entering the eye by a factor of 16. More significantly, the eye switches between 2 different types of photoreceptor cells, cones for daytime vision and rods for nighttime vision. This provides adaptation over a range of approximately 10 million in light intensity. During the day, the cones handle visual processing. These cells, concentrated in the center of the retina, provide sharp color vision but require relatively high light levels to function. There are 3 types of cones, sensitive to different wavelength ranges. L cones peak around 560 nanometers, M cones peak around 530 nanometers, and S cones peak around 420 nanometers. These are often called red, green, and blue cones, though their sensitivities overlap considerably. The brain processes the relative responses of these 3 cone types to determine color. At night, the rods take over. These cells, distributed throughout the retina but absent from the very center, are much more sensitive to light than cones. A single rod can respond to a single photon. However, rods don't provide color, information. They all contain the same light-sensitive pigment called rhodopsin, which peaks in sensitivity around 500 nanometers. This is why nighttime vision is essentially monochrome. We see in shades of gray rather than color. The transition between cone vision and rod vision occurs at light levels called mesopic, between photopic, cone-dominated, and scotopic, rod-dominated. During the day, we're firmly in photopic conditions. During deep night, far from artificial lights, we're in scotopic conditions. Dawn and dusk pass through the mesopic range as the light level changes. During daytime photopic conditions, the eye is essentially saturated with light. The pupil is contracted to limit the amount of light entering. The cones are all responding to the abundant illumination. In this state, the eye can still detect contrast, differences in brightness between adjacent areas, but it requires those differences to be significant. A star, emitting only a minute amount of light compared to the bright sky background, doesn't produce enough contrast to stimulate the visual system above the threshold of detection. Contrast sensitivity is usually expressed as the ability to detect differences in brightness. The Weber contrast is defined as the difference between an object's brightness and the background brightness, divided by the background brightness. For detection, this contrast must exceed some threshold value, typically around 0.01 to 0.02 for large uniform areas, though it can be lower for point sources under ideal conditions. A star during the day must produce enough light at your eye to create contrast against the bright blue sky. The star is a point source, so its light arrives from essentially zero angular size. The sky background has a finite brightness across its entire area. For the star to be visible, its apparent brightness must exceed the sky brightness by a detectable margin, given that the daytime sky has a luminance of 10,000 candelas per square meter or more, and given that even the brightest stars produce only minuscule amounts of light at your eye, the contrast is far too small to detect. The sun's overwhelming brightness and the resulting scattered light filling the atmosphere create an environment where stellar visibility becomes physically impossible for human vision. The mechanism is straightforward. Atmospheric scattering creates a bright background, and stars lack sufficient intensity to produce detectable contrast against that background. The same principles apply to most planets and all but the very brightest celestial objects. Only objects with exceptional apparent brightness, the sun itself, occasionally the moon, rarely the brightest planets, can overcome the limitation. This explanation accounts for the daytime invisibility of stars. The atmosphere fills with scattered sunlight, creating brightness levels that exceed the contrast threshold for stellar detection. At night, when the sun no longer illuminates our portion of the atmosphere, the scattering stops. The background brightness drops dramatically. Against the dark sky, even relatively faint stars produce sufficient contrast to be visible. The transition between these states occurs at dawn and dusk, when the changing solar angle gradually increases or decreases the amount of scattered light in the atmosphere. The human visual system evolved to function across a remarkable range of light levels. From the brightest sunlight to the faintest starlight, the difference in illumination spans approximately 10 orders of magnitude. That's a factor of 10 billion. No artificial sensing system achieves this range without switching between different modes or using multiple sensors. The human eye accomplishes it through a combination of structural adaptations and biochemical processes that adjust sensitivity to match the ambient light level. At the core of vision are photoreceptor cells in the retina, the light-sensitive tissue at the back of the eye. Two types of photoreceptors exist: rods and cones. These cells contain light-sensitive molecules called photopigments that undergo chemical changes when they absorb photons. The changed molecules trigger a cascade of biochemical reactions that ultimately produce electrical signals, which are processed by other retinal cells and sent to the brain via the optic nerve. Cone cells, numbering approximately 6 million to 7 million in each human eye, mediate daytime vision. They require relatively high light levels to function, but provide sharp resolution and color perception. Three types of cones exist, each containing a different photopigment with peak sensitivity at different wavelengths. L cones, sometimes called red cones, peak around 560 nanometers. M cones, sometimes called green cones, peak around 530 nanometers. S cones, sometimes called blue cones, peak around 420 nanometers. The brain compares the relative responses of these three cone types to determine the color of objects. Cones concentrate in the fovea, a small pit at the center of the retina where visual acuity is highest. The fovea spans only about 1.5 degrees of visual angle, roughly the width of your thumbnail at arm's length. When you look directly at something, you're positioning it on your fovea to maximize resolution. The fovea contains only cones, no rods. Moving away from the fovea, cone density decreases rapidly. This is why your peripheral vision, though good at detecting motion, lacks the color sensitivity and sharpness of central vision. Rod cells, numbering approximately 90 million to 100 million in each human eye, mediate nighttime vision. They're extremely sensitive to light. A single rod can respond to a single photon, though typically several photons must be absorbed within a short time window to produce a conscious visual sensation. All rods contain the same photopigment called rhodopsin, which peaks in sensitivity around 500 nanometers in the blue-green portion of the spectrum. Because all rods have the same spectral sensitivity, they don't provide color information. Night vision is essentially monochrome, perceived in shades of gray. These rods are absent from the fovea, but densely packed in a ring surrounding it. The highest rod density occurs about 20 degrees from the center of the retina. This is why astronomers viewing faint objects through telescopes use averted vision. They look slightly to the side of the object rather than directly at it, positioning the image on the rod-rich area rather than the cone-only fovea. The technique makes faint stars visible that would be invisible with direct viewing. The transition between cone vision and rod vision occurs at light levels called mesopic, intermediate between photopic, where cones dominate, and scotopic, where rods dominate. During the day, illumination levels are firmly in the photopic range. Cones handle all visual processing. The rods are present but saturated. They've absorbed so much light that they can't respond to variations. During deep night, far from artificial lights, illumination drops into the scotopic range. Rods handle visual processing. The cones are present but unable to function at such low light levels. The adaptation of the eye to different light levels involves multiple mechanisms operating at different timescales. The fastest mechanism is the pupillary light reflex. The pupil, the circular opening in the center of the iris, adjusts its diameter in response to light level. In bright light, the pupil constricts to about 2 mm in diameter. In darkness, it dilates to about 8 mm. This changes the area of the opening by a factor of 16, which means 16 times more light enters the eye with the pupil fully dilated compared to fully constricted. The pupil responds within about 1 second to changes in light level. While a factor of 16 is significant, it's tiny compared to the billion-fold range of light levels the eye handles. The major adaptation occurs within the photoreceptors themselves through biochemical processes. The most important is the regeneration and bleaching of photopigments. Rhodopsin in rods consists of a protein called opsin bonded to a light-sensitive molecule called 11-cis-retinol, derived from vitamin A. When rhodopsin absorbs a photon, the 11-cis-retinol changes shape to all-trans-retinol. This shape change triggers the phototransduction cascade that produces the electrical signal. The all-trans-retinol then separates from the opsin. The opsin alone is said to be bleached. It can no longer respond to light until it recombines with fresh 11-cis-retinol. The regeneration of rhodopsin requires the all-trans-retinol to be converted back to 11-cis-retinol through a series of enzymatic reactions occurring in the retinal pigment epithelium, the layer of cells behind the photoreceptors. This conversion process takes time. After exposure to bright light that bleaches a large fraction of rhodopsin, full regeneration and recovery of maximum sensitivity can require 30 to 40 minutes. During the day, bright sunlight bleaches rhodopsin continuously. The rods can't keep up. As fast as rhodopsin regenerates, more gets bleached. The rod system remains saturated, unable to contribute to vision. When the sun sets and light levels drop, the bleaching rate decreases. Rhodopsin begins to accumulate. As it does, rod sensitivity increases. This is dark adaptation, the gradual recovery of sensitivity that occurs when moving from bright to dim illumination. Cone photopigments undergo similar bleaching and regeneration, but cones can function even when a substantial fraction of their photopigment is bleached. This gives cones better performance at high light levels. During the day, cone photopigments maintain an equilibrium between bleaching and regeneration that allows continued function. When light levels drop at dusk, cone sensitivity increases as more photopigment accumulates, but cones quickly reach their maximum sensitivity. Rods continue adapting for much longer, eventually surpassing cone sensitivity at low light levels. Additional adaptation mechanisms operate through changes in the biochemical pathways of phototransduction. In bright light, calcium levels inside photoreceptors drop because calcium influx through light-sensitive channels decreases while calcium efflux continues. Lower calcium levels affect multiple processes. Guanylyl cyclase, the enzyme that synthesizes cGMP, the molecule that opens light-sensitive channels, becomes more active in low calcium. This helps restore cGMP levels and reopen channels after they've been closed by light, speeding recovery. Proteins called recoverin and guanylyl cyclase activating proteins mediate these calcium effects. These Adaptation mechanisms adjust the operating point of the photoreceptors to match the ambient light level. In darkness, photoreceptors are highly sensitive, capable of responding to a few photons. In bright light, they're less sensitive but respond faster and over a wider range of intensities. This maintains useful vision across the enormous range of natural illumination. During the day, the visual system operates in photopic mode. The cones handle everything. The bright sunlight and resulting scattered light provide more than enough illumination for cone function. The rods, though present, contribute nothing. Against this backdrop of abundant light, seeing a faint star would require the star's light to produce a response in the cones above the background noise. The background consists of photons from scattered sunlight arriving from all directions. These photons stimulate the cones continuously. A star would need to add enough extra photons arriving from its specific direction to create a detectable increase in cone stimulation. Consider the number of photons involved. On a bright day, illumination at the surface might be 100,000 lux. 1 lux equals 1 lumen per square meter. A lumen is defined such that monochromatic light at 550 nanometers, the peak of photopic luminous efficiency, delivers about 680 photons per second per square millimeter at 1 lux. At 100,000 lux, that's 68 million photons per second per square millimeter. The pupil, at perhaps 3 millimeters diameter in daylight, has an area of about 7 square millimeters. So roughly 500 million photons per second enter the eye from the bright sky. These photons come from all directions, from the entire visible sky. They're arriving continuously, creating a steady background of stimulation. A star, by contrast, is a point source. All its photons arrive from essentially the same direction. Sirius, the brightest star, at magnitude minus 1.46, delivers about 10 billion times fewer photons than the Sun. Even accounting for atmospheric transmission and the collecting area of the pupil, Sirius during the day would contribute only a tiny fraction of the photons entering the eye compared to the scattered sunlight. The star's contribution would be completely swamped by the background. The visual system processes spatial patterns. It detects edges, contrasts, and variations in brightness across the visual field. To see a star, the visual system would need to detect that slightly more light arrives from the star's direction than from the immediately surrounding sky. This requires the star's contribution to exceed the random fluctuations in the background light. Those fluctuations arise from the quantum nature of light. Photons arrive randomly, not in a perfectly steady stream, and from neural noise in the visual system itself. The detectability of a signal against noise follows the principles of signal detection theory. The signal must exceed the noise by a sufficient margin to be reliably detected. For visual detection, this typically requires a signal-to-noise ratio of at least 3 to 5, meaning the signal must be 3 to 5 times larger than the typical fluctuations in noise. In bright daylight, the noise level is high because so many photons are arriving and because the visual system, operating in its photopic mode, is optimized for spatial resolution and speed rather than ultimate sensitivity. Under these conditions, a star lacks sufficient signal strength to overcome the noise. Its photons simply don't add enough to the steady stream of scattered sunlight photons to create a detectable variation. The star remains invisible not because its light doesn't arrive, but because that light creates no perceptible effect on the visual system operating in bright light conditions. At night, everything changes. The sun no longer illuminates the atmosphere. Above your location, scattering ceases. The background light level drops dramatically. In truly dark conditions far from artificial lights, the sky itself becomes essentially black, contributing very few photons. The visual system, through dark adaptation, shifts into scotopic mode. The rods, now recovered from bleaching and maximally sensitive, detect the few photons arriving from stars. A star like Sirius, though delivering vastly fewer photons than the Sun, delivers many more than the dark night sky background. The contrast is reversed. Instead of a faint source against a bright background, you have a bright source against a dark background. The star's photons arrive from a single direction, creating a localized concentration of stimulation in the retina. The visual system easily detects this as a point of light against the darkness. The adaptation of the visual system between day and night represents one of the most remarkable capabilities of human sensory processing. The same retina, the same photoreceptors, function across a billion-fold range of illumination through elegant biochemical and neural mechanisms that continuously adjust sensitivity. During the day, that adaptation renders the visual system essentially blind to stars. At night, it makes even faint stars visible. The stars themselves haven't changed. Your eyes have. The transition from day to night reverses everything we've described. As the sun descends toward the horizon, its light enters the atmosphere at increasingly shallow angles. The path length through the atmosphere increases. More scattering occurs. The direct sunlight takes on warmer hues, yellow, orange, red, as short wavelengths get preferentially scattered away. The sky near the sun blazes with color at sunset, the result of extensive scattering along the long path through the atmosphere. As the sun drops below the horizon, twilight begins. The sky remains illuminated because sunlight still reaches the upper atmosphere. Some of that light scatters downward, providing illumination even though the sun itself is no longer visible. This is civil twilight, lasting until the sun reaches 6 degrees below the horizon. During civil twilight, enough light remains for most outdoor activities. The sky is noticeably brighter than during the day's darkest moments, but stars begin to appear. As twilight deepens, the sun descends further below the horizon. Nautical twilight extends from 6 to 12 degrees below the horizon. During this period, the horizon remains visible at sea, allowing navigators to take sights on stars and the horizon simultaneously. The sky continues darkening. More stars appear. The brightest stars visible during civil twilight are joined by progressively fainter ones. Astronomical twilight extends from 12 to 18 degrees below the horizon. During this final twilight phase, the sun's light still affects the sky's appearance, but most astronomical observations become possible. When the sun reaches 18 degrees below the horizon, twilight ends and night begins. The sky is as dark as it will get at that time and location, limited only by natural air glow, zodiacal light, starlight itself, and any artificial light pollution. The progression of twilight provides an observational window into the phenomenon we've been discussing. During bright civil twilight, no stars are visible except perhaps Venus if favorably positioned. As twilight deepens, stars appear in order of brightness. The magnitude system quantifies this. A first magnitude star like Arcturus appears during civil twilight. A second magnitude star like Polaris appears during nautical twilight. Third magnitude, fourth magnitude, and fainter stars appear progressively as the sky darkens. This sequential appearance results from the decreasing sky brightness. As less sunlight reaches the upper atmosphere, less scattering occurs, and the sky background dims. Each increment of dimming allows slightly fainter stars to produce sufficient contrast for visibility. The process is gradual rather than sudden, reflecting the continuous change in solar angle and atmospheric scattering. For someone observing the evening sky, the transition is peaceful. The bright day sky slowly yields to darkness. The first star appears, then another, then more. Within an hour after sunset, depending on latitude and season, the sky transitions from blue to black, and the full glory of the night sky emerges. The Milky Way, invisible during daylight and twilight, becomes visible as a luminous band. Constellations appear. The apparent motion of the stars, caused by Earth's rotation, becomes noticeable if you watch long enough. This is the moment when the question we started with finds its resolution. During the day, stars were invisible because scattered sunlight filled the atmosphere with light far brighter than starlight. Now, with the sun below the horizon and scattering minimized, the stars reappear. They haven't returned. They were there all along. What's changed is the state of the atmosphere and the adaptation of your eyes. The atmosphere no longer scatters significant sunlight. Your eyes have adapted to darkness, shifting from cone-based photopic vision to rod-based scotopic vision. The stars you see at night vary depending on several factors. Your latitude determines which constellations are visible. Some stars never rise above the horizon from certain locations, while others never set. The season determines which constellations are visible at a convenient evening time. Earth's motion around the sun means different portions of the night sky face away from the sun at different times of year. In summer, you see different constellations than in winter. Light pollution affects visibility dramatically. From a city, the artificial lights, street lights, building lights, advertising signs, create their own form of sky brightness. Light from these sources scatters in the atmosphere just as sunlight does. This artificial scattered light creates a background against which faint stars cannot be seen. In major cities, perhaps only a few dozen of the brightest stars remain visible. The Milky Way disappears entirely. Many people living in urban areas have never seen a truly dark sky. From a dark rural location far from cities, the night sky looks profoundly different. Thousands of stars become visible. The Milky Way is prominent. The sky seems crowded with stars rather than sparse. This is the natural state of the night sky, the view that humans experienced throughout most of history before electric lighting became widespread. It's the view that guided navigation, inspired mythology, and provided the data for early astronomy. The number of stars visible to the naked eye under perfect conditions is often stated as around 6,000 total, about 3,000 visible from any one location, since half the sky is below the horizon. This includes all stars down to magnitude 6.0 or so. In reality, from even good dark sky sites, the number visible is usually lower, perhaps 2,000 to 3,000, because atmospheric extinction, especially near the horizon, dims stars, and because human visual acuity has limits. But regardless of the exact number, the difference between a city sky showing dozens of stars and a rural sky showing thousands is profound. The moon's phase affects visibility too. During full moon, the bright lunar surface reflects substantial sunlight. This reflected light scatters in Earth's atmosphere, brightening the night sky. The effect is strong enough to render faint stars invisible. Many deep sky objects that require dark skies for observation, galaxies, nebulae, faint star clusters, disappear in moonlight. Serious amateur astronomers often plan observations around the moon's phase, favoring the nights around new moon when the sky is darkest. But even on a moonlit night, bright stars remain visible. The moon itself shines at magnitude -12.6 at full phase, far brighter than any star but far fainter than the sun. The resulting sky brightness from scattered moonlight is enough to hide faint stars but not enough to overwhelm the brightest ones. This provides another demonstration of the principle. Background brightness determines visibility, and objects must produce sufficient contrast against that background. So, as night arrives and deepens, the phenomenon of invisible stars reverses. The mechanism remains the same. Scattered light creates background brightness that must be overcome for an object to be visible. What changes is the intensity of the scattered light. During the day, intense sunlight creates intense scattering, producing a bright sky that hides stars. During the night, with no sunlight to scatter, the sky darkens and stars emerge. The elegance of this explanation lies in its simplicity. A single mechanism, Rayleigh scattering, explains both the blue sky of day and the black sky of night. A single principle, contrast detection, explains both the invisibility of stars during the day and their visibility at night. The night sky isn't actually completely black. Even on a perfectly clear night, far from any artificial lights and under new moon, the sky has a faint brightness. Several sources contribute to this natural sky glow. The most significant is air glow, a faint emission of light by atoms and molecules in the upper atmosphere. Air glow results from chemical reactions and the recombination of molecules that were broken apart by solar ultraviolet radiation during the day. It's distinct from aurora, which occurs when charged particles from the sun interact with the atmosphere near the poles. Airglow is quite faint, typically producing a sky brightness of about 250 magnitudes per square arc second in the visible spectrum. This translates to roughly 0.001 candelas per square meter, about 10,000 times dimmer than the daytime sky. It's barely perceptible to human vision, though sensitive instruments detect it easily. The intensity and spectrum of airglow vary with location, time of night, and season. Airglow can be strong enough to affect astronomical observations, especially for detecting very faint objects. Zodiacal light contributes additional brightness. This is sunlight scattered by interplanetary dust particles in the plane of the solar system. The dust consists of tiny particles left behind by comets and asteroids. It extends throughout the solar system but concentrates near the ecliptic, the plane of Earth's orbit. Zodiacal light appears as a faint, diffuse cone of light extending along the ecliptic, most visible in the west after sunset or in the east before sunrise during spring and autumn, when the ecliptic makes a steep angle with the horizon. Starlight itself contributes to sky brightness. Although individual faint stars may not be visible to the naked eye, their collective light adds to the sky glow. This is particularly true of the Milky Way, where billions of distant stars too faint to resolve individually combine to create a luminous band across the sky. The diffuse glow of the Milky Way represents countless faint stars, along with emission from interstellar gas clouds. Even accounting for these sources, the natural night sky is extraordinarily dark compared to day. The total natural sky brightness on a moonless night might be around 0.003 candelas per square meter at the zenith, roughly 5 million times darker than the daytime sky at 10,000 candelas per square meter. This vast difference explains why stars invisible during the day become visible at night. The stars themselves exhibit a range of brightness. The magnitude scale quantifies this, with each magnitude step representing a brightness factor of approximately 2.512. A first magnitude star is about 2.5 times brighter than a second magnitude star, which is about 2.5 times brighter than a third magnitude star, and so on. The scale extends to negative numbers for very bright objects. Sirius at magnitude -1.46 is about 4 times brighter than a zero magnitude star like Vega. Under perfect conditions, the faintest stars visible to the naked eye reach about magnitude 6.5. This represents the limit of human visual sensitivity to point sources against a dark background. In practice, most people under good conditions see stars to magnitude 6.0, with some variation based on individual visual acuity and atmospheric conditions. The magnitude 6 threshold means that stars about 250 times fainter than a first magnitude star remain visible. The number of stars visible increases rapidly with decreasing brightness because faint stars are far more numerous than bright ones. Only a few dozen stars reach first magnitude or brighter. A few hundred reach second magnitude or brighter. A few thousand reach fourth magnitude or brighter. The relationship is approximately logarithmic. Each magnitude fainter includes about 4 times more stars than the magnitude above it. This distribution of stellar brightness results from the combination of stellar intrinsic luminosity and distance. Stars vary enormously in intrinsic brightness. The most luminous stars, supergiants like Deneb or Betelgeuse, radiate hundreds of thousands of times more energy than the Sun. The least luminous stars, red dwarfs, radiate just a tiny fraction of the Sun's energy. Distance then modifies apparent brightness according to the inverse square law. Most stars we see in the night sky lie within a few hundred light-years of Earth. This is a tiny fraction of the Milky Way's diameter of about 100,000 light-years. We're seeing only the nearest neighborhood of stars. More distant stars, even if intrinsically bright, appear too faint to see with the naked eye. Exceptions include the most luminous supergiants, which can be visible from thousands of light-years away because their enormous intrinsic brightness compensates for distance. The visibility of stars at night depends critically on the darkness of the sky background. Consider a third magnitude star, easily visible from a dark site. Its light produces a certain amount of stimulation in the rod cells of your retina. The dark sky background produces only minimal stimulation. The contrast between the star and the background is strong, making the star clearly visible. Now imagine the sky brightness increasing, perhaps from scattered moonlight or artificial light pollution. The background stimulation increases. The star's stimulation remains the same. The contrast decreases. At some point, the contrast falls below the detection threshold, and the star disappears from view even though its light still arrives at your eye. This is precisely what happens at dawn. As twilight begins and the sky brightness increases from scattered sunlight, faint stars disappear first. Then progressively brighter stars vanish as the sky brightness continues increasing. By the time full daylight arrives, even the brightest stars lack sufficient contrast to be visible. The progression reverses at dusk, with stars appearing in order from brightest to faintest as the sky darkens. The blackness of the night sky itself has astronomical significance. Known as Olbers's paradox, the question asks why the night sky is dark if the universe contains infinite stars. If the universe were infinite in both space and time, with stars distributed uniformly, then every line of sight from Earth should eventually intersect a star's surface. The entire sky should glow as brightly as the surface of a star. The fact that it doesn't suggests either that the universe is finite in age or that it's expanding so that light from very distant stars is redshifted out of the visible spectrum, or both. The modern resolution of Olbers's paradox involves both cosmology and observational astronomy. The universe is indeed old but not infinite in age, about 13.8 billion years. Light from more distant stars simply hasn't had time to reach us yet. Additionally, the universe is expanding, which causes distant light to redshift to longer wavelengths and reduces the intensity of light from very distant sources. These factors combine to ensure that the night sky remains dark despite the existence of countless stars and galaxies. For our purposes, the darkness of the night sky is what allows stars to be visible. During the night, without sunlight to scatter, the atmosphere becomes transparent. The natural sky glow from air glow and zodiacal light is faint enough that stars create strong contrast. The adapted rods in your eyes detect the starlight easily. The visual system processes the spatial pattern of stars, creating the familiar appearance of constellations and the Milky Way. This visibility depends on the same principles that govern invisibility during the day. Light must produce contrast against a background. The brightness of the background determines what can be detected. During the day, scattered sunlight creates a bright background that overwhelms starlight. During the night, the dark background allows starlight to dominate. The stars themselves are unchanged. They continue radiating the same amount of energy, sending the same number of photons toward Earth. What changes is whether those photons can be perceived against the background light level and given the adaptation state of the human eye. We can now assemble the complete explanation for why stars vanish during the day and reappear at night. The explanation involves several interconnected elements: the nature of sunlight, the composition and structure of the atmosphere, the physics of Rayleigh scattering, the brightness levels involved, and the capabilities of human vision. Each element contributes to the overall picture, and understanding their relationships provides a thorough answer to the question. Sunlight arrives at Earth as electromagnetic radiation across a broad spectrum of wavelengths. The visible portion, from about 390 to 700 nanometers, contains the light we perceive directly. The Sun's surface temperature of approximately 5,800 Kelvin produces a blackbody spectrum that peaks in the visible range with substantial energy across all visible wavelengths. The solar constant, approximately 1,361 watts per square meter at the top of the atmosphere, quantifies the intensity of this radiation. Earth's atmosphere consists primarily of nitrogen and oxygen molecules, with trace amounts of argon, carbon dioxide, and other gases. These molecules are extremely small, typically about 0.3 nanometers in diameter, which is hundreds of times smaller than visible light wavelengths. The atmosphere extends from the surface to an altitude where it gradually merges with space, but most of its mass concentrates in the troposphere, the lowest layer extending to approximately 10 to 15 kilometers altitude depending on latitude. When sunlight enters the atmosphere, it encounters these countless molecules. Some light passes through without interaction. Some gets absorbed, particularly ultraviolet radiation absorbed by ozone in the stratosphere, and some gets scattered by the molecules. This scattering redirects light from its original path into new directions. The scattering is elastic, meaning photons don't lose energy, but their direction changes. The amount of scattering depends strongly on wavelength according to Rayleigh's law, which states that scattering intensity is inversely proportional to the fourth power of wavelength. Blue light at 450 nanometers scatters about 4.4 times more efficiently than red light at 650 nanometers. This wavelength dependence means short wavelength light scatters preferentially. When white sunlight enters the atmosphere, the blue and violet components scatter much more than the red and orange components. This preferential scattering creates the blue sky. When you look at any point in the sky away from the sun, you see light that has been scattered by air molecules in that direction. Since short wavelength blue light scatters most, the scattered light appears blue. The effect accumulates through the thickness of the atmosphere. The more atmosphere light travels through, the more scattering occurs. When the sun is low on the horizon, sunlight travels through more atmosphere, leading to more extensive scattering and the warm colors of sunrise and sunset. The scattered blue light fills the daytime sky with brightness. On a clear day with the sun high in the sky, the zenith sky brightness reaches approximately 10,000 candelas per square meter or more. This represents an enormous amount of light compared to the dark night sky. The source of this brightness is sunlight. The sun's intrinsic luminosity and its proximity to Earth make it billions of times brighter than any other star. When the sun's light scatters throughout the atmosphere, it creates a background brightness that exceeds the apparent brightness of distant stars. Stars continue radiating and sending photons toward Earth during the day just as they do at night. Their intrinsic brightness hasn't changed. The photons still travel through space at the speed of light, still enter Earth's atmosphere, and still reach the ground. But these photons must now compete with the scattered sunlight. When you look toward a star during the day, the light entering your eye comes predominantly from scattered sunlight arriving from all directions, with only a minuscule additional contribution from the star's direct light. The human visual system detects objects by processing contrast, differences in brightness between adjacent regions of the visual field. To see a star, the star's light must produce enough additional brightness from its direction compared to the surrounding sky to exceed the detection threshold. During the day, operating in photopic mode with cone cells, the visual system is adapted to bright light and optimized for spatial resolution and speed rather than ultimate sensitivity. The detection threshold requires significant contrast, typically several percent. A star like Sirius, the brightest star visible from Earth, has an apparent magnitude of -1.46. The Sun, by comparison, has an apparent magnitude of -26.7. The difference of about 25 magnitudes represents a brightness factor of approximately 11 billion. Even accounting for atmospheric scattering, absorption, and the directional nature of starlight versus diffuse sky brightness, the scattered sunlight, overwhelms the starlight by an enormous factor. The star's contribution to the light entering your eye is negligible compared to the scattered sunlight. As a result, stars are invisible during the day. Not because they've disappeared, not because their light is blocked, but because their light lacks sufficient intensity to produce detectable contrast against the bright scattered sunlight filling the atmosphere. The physical mechanism is straightforward. Rayleigh scattering creates a bright background, and stars cannot overcome that background. The same principle applies to most planets and other celestial objects. Only the most extremely bright objects, the sun itself, occasionally the moon, rarely the brightest planets under ideal conditions, produce enough light to remain visible. As evening approaches and the sun descends toward the horizon, the situation begins to change. The sun's light enters the atmosphere at increasingly shallow angles, traveling through more atmosphere, before reaching your location. Scattering increases along this extended path, giving sunrises and sunsets their characteristic colors. Once the sun drops below the horizon, twilight begins. Sunlight still reaches the upper atmosphere, and scattered light from these upper layers continues illuminating the sky, but the intensity gradually decreases as the sun sinks deeper below the horizon. During twilight, sky brightness decreases continuously. As it does, stars begin to appear. The brightest stars and planets appear first during civil twilight. Progressively fainter stars appear as twilight deepens through nautical and astronomical phases. Each star becomes visible when the sky background dims enough that the star's light produces sufficient contrast. The progression continues until twilight ends, approximately 90 minutes after sunset, depending on latitude and season, and full night arrives. At night, the mechanism that made stars invisible during the day reverses. Sunlight no longer illuminates the atmosphere above your location. Scattering of sunlight ceases. The sky background brightness drops to the natural nighttime level, which includes airglow, zodiacal light, and the diffuse glow of countless faint stars, but totals only about 0.003 candelas per square meter, roughly 5 million times darker than the daytime sky. Against this dark background, stars become easily visible. The same stars that were present but invisible during the day now stand out clearly. The photons arriving from distant stars, though vastly fewer than photons of scattered sunlight during the day, now dominate over the minimal background. The contrast is strong. The adapted eye, now operating in scotopic mode with rod cells maximally sensitive after dark adaptation, detects even relatively faint stars easily. The human visual system has also adapted. During the day, in bright light, the cone cells handled vision, optimized for color perception and high spatial resolution. At night, the rod cells take over, providing extreme sensitivity at the cost of color information and some resolution. The pupils have dilated from about 2 mm to about 8 mm, increasing the light gathering area by a factor of 16. Rhodopsin in the rods has regenerated after being bleached during the day, restoring maximum sensitivity. These adaptations enable night vision that can detect stars down to about magnitude 6, representing about 3,000 stars visible at any one time from a given location. The complete cycle, stars visible at night, disappearing at dawn, invisible during day, reappearing at dusk, results from this interplay between atmospheric scattering, solar brightness, and visual adaptation. The same atmospheric molecules that make the sky blue during the day make stars invisible by filling the atmosphere with scattered light. The same dark adaptation that allows you to navigate in dim indoor lighting allows you to see faint stars under the night sky. The same principles of contrast detection that allow you to read text on a page explain why stars need a dark background to be visible. Nothing about this explanation is mysterious once you understand the components. Light scatters when it encounters matter. The amount of scattering depends on wavelength and particle size. Small particles scatter short wavelengths preferentially. The atmosphere contains vast numbers of small molecules. Sunlight contains all visible wavelengths. When sunlight passes through the atmosphere, blue light scatters more than red, filling the sky with blue light. This scattered light is bright enough to overwhelm the light from distant stars. At night, without sunlight to scatter, the sky darkens and stars become visible. The explanation requires no special phenomena, no unusual processes. It involves only well-understood physics, electromagnetic radiation, elastic scattering, the inverse fourth power wavelength, dependence of Rayleigh scattering, the inverse square law for light intensity with distance, the physiology of human photoreceptors, and the principle of contrast detection. These elements combine to produce the observed effect. Stars vanish during the day and reappear at night. The beauty of this explanation lies in its universality. The same principles apply everywhere on Earth. Someone standing at the equator sees the same effect as someone standing at the poles. The specific stars visible differ due to latitude, and the timing of twilight differs due to the angle of the sun's path, but the mechanism remains identical. Scattering by atmospheric molecules creates daytime sky brightness. That brightness hides stars. The absence of scattering at night allows stars to be visible. The explanation also connects to broader astronomical concepts. The brightness of stars, quantified by the magnitude scale, determines which stars remain visible under various conditions. Light pollution, essentially artificial daytime created by human lighting, demonstrates the same principle. Add brightness to the night sky, and stars disappear. The expansion of the universe and the finite age of the cosmos explain why the night sky is dark rather than uniformly bright. The adaptation of the human eye illustrates the remarkable capabilities of biological sensors. And so, the mystery resolves. Stars don't disappear during the day. They remain exactly where they've always been, continuing their patient existence across the vast distances of space. Their light continues streaming toward Earth, photons completing journeys that may have begun years or centuries ago. What changes is not the stars, but the conditions through which we observe them. The atmosphere, illuminated by our nearest star, becomes filled with scattered blue light. Against that bright background, distant stars fade from view. When night returns and the atmosphere darkens, the stars emerge once again, visible as they've been for billions of years, waiting patiently for darkness to reveal them. The rhythm of day and night, of blue skies and starry darkness, has shaped human experience throughout our existence. The rising sun brings light and warmth. The setting sun brings coolness and darkness. The stars appear at night, reliable markers of time and season. These patterns seemed unchangeable, built into the fabric of reality. And, in a sense, they are, but they're not arbitrary. They result from physical laws operating in specific conditions. The atmosphere that sustains life also transforms our view of the cosmos. Those same molecules of nitrogen and oxygen that we breathe, that enable fire and metabolism, scatter sunlight and create the blue sky. The scattering that makes daytime vision possible also obscures our view of the universe beyond. It's a trade-off, though not one we had any say in. The atmosphere was here long before humans evolved. Its properties emerged from planetary formation and the evolution of Earth's climate. We simply inherited the conditions and adapted to them. Other worlds show different conditions. The moon, lacking an atmosphere, displays a black sky even in full sunlight. Astronauts walking on the lunar surface during the Apollo missions could see stars whenever they looked away from the sun and Earth, regardless of the time of day. The photographs show this clearly: a black sky with the sun visible as an extremely bright disk, and stars visible in the portions of sky away from the sun and the bright lunar surface. The absence of scattering makes the difference. Mars, with its thin atmosphere composed mainly of carbon dioxide, shows yet another variation. The Martian sky appears butterscotch or tannish pink during the day rather than blue. This color results from scattering by fine dust suspended in the atmosphere rather than molecular scattering alone. The dust particles are larger than molecules, placing them in a different scattering regime where wavelength dependence is weaker. Sunsets on Mars appear blue rather than red, the opposite of Earth, because the dust scatters red light more than blue at the shallow angles characteristic of sunset. Stars would be more easily visible during Martian day than during Earth's day because the atmosphere is thinner and scatters less light, though the dusty sky still provides some background brightness. Venus, with its thick atmosphere of carbon dioxide and clouds of sulfuric acid, presents the opposite extreme. The atmosphere is so dense and the clouds so opaque that the surface never receives direct sunlight, only diffuse illumination through the clouds. From the surface, you would never see the sun as a distinct disk, much less any stars. The sky would appear uniformly bright during day, glowing with scattered light, and perhaps marginally darker at night, but never truly dark. No stars would ever be visible from the surface of Venus. These variations emphasize that Earth's particular characteristics, the composition and density of the atmosphere, the intensity of sunlight at our orbital distance, the resulting color and brightness of the daytime sky, are specific to our planet. The principle of scattering is universal, but its effects depend on local conditions. The same physics operates everywhere, but the outcomes differ based on atmospheric composition, pressure, and illumination. Understanding why stars vanish during the day provides insight into these broader questions about atmospheres, light, and observation. It demonstrates how phenomena that seem self-evident or even magical often have straightforward physical explanations once you examine the mechanisms involved. The blue sky isn't blue because that's just how skies look. It's blue because nitrogen and oxygen molecules scatter short-wavelength light preferentially according to the inverse fourth power law derived by Rayleigh. The stars don't vanish at dawn because they're daytime sensitive. They become invisible because scattered sunlight creates a bright background that overwhelms their faint light. This type of understanding, moving from observation to mechanism, from what happens to why it happens, characterizes the scientific approach. It doesn't diminish the beauty or wonder of the phenomena. If anything, it enhances them. Knowing that the blue sky results from countless quadrillions of molecular scattering events, each following the laws of electromagnetism, each contributing infinitesimally to the overall effect, reveals an elegance that simple acceptance never could. Knowing that stars remain present above you during the day, invisible only because atmospheric scattering creates a bright background, connects you more directly to the cosmos than assuming they simply disappear. The next time you look at the daytime sky, you might think about the photons arriving from the sun, traveling 8 light minutes across space, entering the atmosphere, encountering nitrogen and oxygen molecules, scattering in random directions, and eventually reaching your eyes as blue light. You might think about the stars positioned above you right now, their light arriving continuously but invisible against the bright background. You might think about how twilight gradually shifts the balance, dimming the scattered sunlight, allowing stars to emerge one by one as contrast permits. And on a clear night, far from city lights, when you look up at the Milky Way stretching across the sky, you might think about the dark adaptation of your eyes, the rhodopsin regenerating in your rod cells, the quantum efficiency that allows single photons to produce neural signals. You might think about the darkness of the sky, the minimal background that allows even faint stars to be visible. You might think about how this same sky, just hours ago, was bright blue and opaque, hiding the very stars that now seem so prominent. The phenomenon is simple in principle. Light scatters when it encounters matter, creating brightness that can hide fainter sources. The execution is complex. Specific wavelength dependencies, particular atmospheric compositions, precise brightness levels, sophisticated visual adaptations. But the result is the everyday experience we all share, the blue sky of day hiding the stars, the black sky of night revealing them. Understanding the mechanism doesn't change the experience. The sky still appears blue, stars still emerge at dusk, but the understanding adds a layer of appreciation, a recognition that even familiar phenomena operate according to discoverable principles. So the stars remain where they've always been, day and night, visible or invisible, constant in their positions relative to one another, slowly wheeling across the sky as Earth rotates. The atmosphere remains what it's always been, a thin shell of gas that sustains life and transforms our view of the universe. The physics remains what it's always been, unchanging laws governing how light interacts with matter, and we remain what we've always been, observers trying to understand our place in the cosmos, finding elegance and order in the phenomena we perceive. Thank you for joining this exploration of why stars disappear during the day and reappear at night. The explanation, as we've seen, involves atmospheric scattering, the brightness of the sun, the physics of light, and the capabilities of human vision, all working together to create the familiar cycle of day and night skies. If you found this journey through the physics of atmospheric scattering interesting, you might enjoy exploring other topics on this channel. Nebula Nights covers various aspects of astronomy and cosmology, always aiming for the same combination of scientific accuracy and calm presentation. Each video explores a different aspect of the universe, from the very small to the very large, from the nearby to the distant. Consider subscribing if you'd like to continue these quiet explorations of space and science. The channel offers a place to learn about the cosmos without urgency, without excitement, just steady information delivered at a pace that supports both learning and relaxation. Subscribing ensures you'll see new videos as they're released, allowing you to build understanding gradually across multiple topics. If you appreciated the depth and thoroughness of this explanation, a like helps the video reach others who might appreciate the same approach. The algorithm tends to favor engagement, and likes signal that the content succeeded in its goal of providing thorough, accurate explanation in a calm format. It's a simple way to support the channel's continued creation of detailed scientific content. Comments are welcome if you have questions, corrections, or thoughts about the content. While the research for each video aims for accuracy, astronomy and physics are vast fields, and additional perspectives or clarifications from viewers can add value. The community around the channel includes people with various backgrounds and interests, and their contributions often enhance the discussion. Thank you again for spending this time exploring the physics of the daytime sky and the visibility of stars. The universe continues its patient existence, vast and intricate, filled with phenomena that reward careful examination. May your own observations of the sky, whether by day or night, be enriched by understanding the mechanisms at work. Clear skies and good night.